In this video, we're going to be looking at determinants and Cramers Rule. And what we're going to be doing here in this video is evaluate a second order determinant. Also, we'll be solving a system of linear equations in two variables using the concept of Cramers Rule. And the third thing we'll look at is evaluate a third order determinant. Okay, now let's look at the determinant of a 2 by 2 matrix. And sometimes it's called a square matrix. So here the determinant is a real number associated with every square matrix. And the determinant of a 2 by 2 square matrix is defined as follows. And in this case, this is the definition here. And of course, before I give you this definition, let me tell you what a square matrix is. The number of rows and the number of columns must be the same. So a square matrix in this case would be a 2 by 2 matrix or a 3 by 3 matrix. 3 rows, 3 columns. And for a 2 by 2 matrix, 2 rows, 2 columns. So the determinant of the matrix A1B1 and A2B2 is defined as this with the vertical bars, or it's denoted by the same elements with the vertical bars, and it's defined by this. We take the product of this main diagonal from the upper left to lower right minus this diagonal from the lower left to the upper right. Okay, and that's going to be A1B2 minus A2B1. We also say that the value of the second order determinant is this, A1B2 minus A2B1. Okay, now here, to evaluate the second order determinant, you find the difference of the product of the two diagonals here. So we're finding the product of this first diagonal from the upper left to the lower right minus the product of this diagonal from the lower left to the upper right. That's A1 times B2 minus A2 times B1. That's how we evaluate a second order determinant. Okay, now let's look at a couple of examples here on how to evaluate determinants. Here we got two matrices, and we're going to evaluate the determinant for each of the following matrices. Okay, and I'm going to write this on my whiteboard. Here we got, in this case here, we got 10, 9, 6, 5. And here we want to evaluate the determinant of this matrix. Now we can call this matrix A if we want to. So here we'll say the determinant, which is the DET, which is the abbreviation for the determinant of A, would just be just with the vertical bars. And the way we find the determinant is this. We take the product of this diagonal from the upper left to the lower right. So in this case here, we're taking the product of 10 and 5. And we're going to subtract from it the product of this diagonal from the lower left to the upper right. That's 6 times 9. So here, if we do 10 times 5, that's going to give us 50 minus 6 times 9, which is 54. So 50 minus 54 would give us -4. So the determinant of this matrix here, 10, 9, 6, 5, would be -4. Okay, that's how we find the determinant of a square matrix or a 2 by 2 matrix. Okay, another example would be this. Let's say we had 4, 3, and then -5, -8. 4, 3, -5, -8. And here we want to find the determinant of this particular matrix. And I'm going to call this matrix B here. So here, the determinant of matrix B would be the same numbers just with the vertical bars. And in this case here, we do the same thing. We take the product of this diagonal from the upper left to lower right, 4 times -8. And it's going to be minus the product of this diagonal from the lower left to the upper right. In this case, that's -5 times 3. Now, when we simplify that, 4 times -8, that's -32, minus 5 times, -5 times 3, that would be -15. So here you got -32 minus -15, which is the same as saying -32 plus 15, which will give you -17. So the determinant of this square matrix would be -17. Okay, now that's how we evaluate the determinant of any 2 by 2 matrix. Okay, now we're going to use this concept of evaluating a square matrix to solve systems of linear equations that are in 2 variables using what they call determinants. Okay, so here determinants can be used to solve a linear system in 2 variables. And this method of using determinants to solve a linear system is called Cramers Rule. Okay. And on this slide, here we have the way that we use Cramer's Rule to solve a system of linear equations in 2 variables. So here, if a1x plus b1y equals c1, and a2x plus b2y is equal to c2, then we can say that x would be this, c1, c2, b1, b2, divided by this determinant of a1, a2, b1, b2. And y is going to be the determinant of a1, a2, c1, c2, divided by a1, a2, divided by a1, a2, b1, b2, where the determinant of a1, a2, b1, b2 is not equal to 0. Now, that might be a little bit confusing, but what does all of this mean? Okay, here's some helpful tips. There are 3 determinants that are used to find x and y. The determinants in the denominators for x and y are identical. So the determinants in the numerators for x and y will differ. So in the abbreviated notation, we write this. X is equal to the determinant for x divided by the determinant, and y is equal to the determinant for y divided by its main determinant, where d is not equal to 0. Okay? So how do we find d? How do we find d of x? And how do we find d of y? Okay? The elements of d, which is the determinant in the denominator, are going to be just the coefficients of the variables in that system. So here, a1, a2, b1, and b2, those comes from the coefficients of x and y, respectively. a1 and a2 are from the coefficients of x. b1 and b2 comes from the coefficients of y. Now, determinant of x, or d of x, is the determinant in the numerator of x. And that's obtained by replacing the coefficients of x in d. with the constants on the right sides of the equations, which are C1 and C2. So this is D. D of x, you're going to replace these coefficients of x with those constants, C1 and C2. So D of x will have C1 and C2, and you'll still have the B1 and B2, which are your coefficients of y. And then the determinant for y, that's D sub y, that's the determinant for in the numerator for y, is going to be obtained by replacing the y coefficients with your constants on the right side of the equations, C1 and C2. So this is D. So now you're going to replace these constants, or these coefficients for y, with your constants. So you still have A1 and A2, which are your coefficients of x. But for your y's, you're going to replace that with your constant C1, C2. That's what's going to give you the determinant for y. Okay. Now let's look at an example of how to use this concept to solve a system of linear equations here. Let's say we had this. 2x minus 3y is equal to negative 11, and x plus 2y is equal to 12. And here I want to use Cramers Rule to solve this system. So what I'm going to do here on a piece of paper, rewrite this system. Here we got 2x plus 3 minus 3y 2x minus 3y equals negative 11. And then the second equation is x plus 2y is equal to 12. Okay. So there are three things we're going to evaluate. Okay. We need D, and then we're going to need D sub x and D sub y. And those are represented by determinants. The D will come from the coefficients of x and y. That's this first column is your coefficient of x, so you got a 2 and a 1 here, so that's going to be this, 2, 1. The coefficients of y are negative 3 and 2. And then let's set up the D sub x, which is going to be this. You're going to this column is usually your first column is your x, but you're going to replace that with your constants here. That's negative 11 and 12. Your y's are going to remain the same, negative 3 and 2. Now for D sub y, your y coefficients will be replaced with those constants. So the y column will become negative 11 and 12. Your x's will remain the same, 2 and 1. Okay? So if you can remember the pattern for D, you're going to have x and y. But for D of x, you're going to have the constants and then y. Then D sub y, you're going to have x and your constants. Okay? But for D, it's always x and y. Let's find the determinants for all three of these. Let's start off with your determinant for D. Of course, we do 2 times 2, the upper left to the lower right, the product of that, 2 times 2, that's 4, minus the product of this diagonal, 1 times negative 3, which is negative 3. So now you got 4 minus negative 3, which will be 7. So that's the determinant for D. Now the determinant for D sub x is this. This diagonal from upper left to lower right, negative 11 times 2, that's negative 22, minus the product of this diagonal, 12 times negative 3, is negative 36. And then negative 22 minus 36 is the same as negative 22 plus 36, which will be 14. And then d sub y is determinant. This is 12 times 2, or 2 times 12. That's going to be 24, minus the product of this diagonal. 1 times negative 11 is negative 11. So 24 minus negative 11, or 24 plus 11, would be 35. Okay. So now, using these, d sub x, and d sub y, I can find out what x is. In this case, x is going to be the determinant of x divided by the determinant, which is d. In this case, d sub x, that's 14, divided by d, which is 7. So 14 divided by 7 is 2. And then for y, it's going to be d sub y divided by d. And in this case, d sub y is 35, divided by d. Of course, that's still 7. So now you got 35 divided by 7, which is 5. Okay? So that's my ordered pair for this system of equations. X is 2 and y is 5. So that solution is that ordered pair 2, 5. And that's all there is for solving a system of equations using Cramers Rule. Okay. All right, here's another example. Let's say I had this. Okay, by the way, let me erase this. Okay, again, I'm going to use Cramer's Rule to solve this system. Here we got 5x plus 4y is equal to 12, and then 3x plus 6y is equal to 24. Okay, and I'll rewrite this. And we're going to do this using Cramer's Rule as well. So here we got 5x plus 4y is equal to 12, and then 3x plus 6y is equal to 24. Okay, that's my system of equations that I'm going to use to solve using Cramer's Rule. So I need to know what d is. I need to know what d sub x is going to be, and d sub y. Now, if you recall, d is always the coefficient of x and y, so you can write x and y on top if you like. That way you'll be able to remember it. And then for d sub x, you're replacing the x with your constants, and then you'll still have your coefficients for y. And then for d sub y, it'll be x here in this column, and then the y column will be replaced with your constants. So this can pretty much help you remember what goes where. The coefficient of x will be these two numbers here, 5 and 3. That goes in this column. And for the y's, your coefficients for y's are 4 and 6. Now for d sub x, let's find out what that matrix is going to look like. The constants are going to be 12 and 24. And then for the y's, your coefficients are still 4 and 6. And then for d sub y, your x coefficients are 5 and 3. And then your constants, your y's, your coefficients for y's will be replaced by your constants, which are 12 and 24. So now we can find the determinants for each one of those. For the determinant for d, start with this diagonal from the upper left to lower right. 5 times 6, that's 30. Minus 3 times 4, that's 12. So 30 minus 12 is 18. And then for d sub x, take this the product of this diagonal from the upper left to lower right. 12 times 6, that's 72. Minus 24 times 4, that's this diagonal from the lower left to the upper right. That's 96. So 72 minus 96 will give you negative 24. And then the determinant for y, that's this matrix here, upper left to lower right, 5 times 24, that's 120, minus this diagonal, 3 times 12, that's 36. So 120 minus 36 is 84. Okay, so let's use these to find out what x and y are going to be. In this case, x is always the determinant of x divided by d, or d sub x divided by d. So d sub x is negative 24, d is 18. So we got negative 24 over 18. We're going to have to reduce that to negative 4/3. Okay, and then for y, that's d sub y divided by d. And in this case, so d sub y is 84, and d is 18. So now we got 84 over 18. We can reduce that to 14 over 3. The numerator and the denominator, we have to divide that by 6. Okay, so those represents the ordered pairs that will satisfy this solution, this system of equations here. So that solution set would be this ordered pair, negative 4/3, 14 over 3. So that's my solution set to this system of linear equations. Okay. All right, now let's look at some special conditions here. All right, in this case here, let's say we have inconsistent and dependent systems. Now, the first condition is this. If your determinant, which is the determinant in your denominator, if that's equal to 0, and at least one of the determinants in the numerator is not 0, then the system is inconsistent. That means that the solution set would be the empty set. And that's a circle with a slash there, meaning the empty set. And then number 2, if your determinant is equal to 0 and all the determinants in the numerator are 0, then the equations in that system are dependent. In other words, that system has infinitely many solutions. And we're going to look at a couple of examples that deal with inconsistent and dependent systems. Okay, so let's look at this example right here. Let's say we want to use Cramers Rule to solve this system. In this case here, we got 3x plus 3y is equal to 2, and 2x plus 2y is equal to 3. And we want to solve this system of equations using Cramers Rule. So in this case here, let's write this down. 3x plus 3y is equal to 2. 2x plus 2y is equal to 3. Here we want to solve this using Cramers Rule. So we know we're going to need d, and we know we're going to need d of x, and also we're going to need d sub y. And of course for d, you know you have your coefficient of x and y, so we can write x and y in each column. D sub x, we replace the x with the constants, and we still have our y's. But for d sub y, we still have our x's, but the y's are replaced with the constants. Okay? Let's start off with a D matrix. Coefficient of x are 3 and 2. The coefficients for your y's are 3 and 2. For d sub x, the constants are going to be replaced with 2 and 3. And for the y's, it's still 3 and 2. And then d sub y, your x's are 3 and 2. But the y's will be replaced with 2 and 3. Okay, so let's find the determinants for each one of these. For the d, 3 times 2 is 6, minus 3 times 2, that's 6. And if we do 6 minus 6, it's going to give you 0. Okay, but let's do d of x and then d sub y. For d of x, 2 times 2, that's 4. Minus 3 times 3, that's going to be 9. So 4 minus 9, that's negative 5. And then d sub y, 3 times 3, that's 9. Minus 2 times 2, that's going to be 4. And then 9 minus 4 would give you 5. Now, let's look at this here. Notice that the d, that's the determinant of d, is 0. The other determinants are not zeros here. Now, notice we're going to get a 0 in the denominator here, because when we do d sub x, well, let's see here. When we do x, which is equal to d sub x divided by d sub x is going to be negative 5, but d is going to be 0. Here we're going to have a 0 in the denominator. And division by 0 is undefined. And the same holds true if we did for y, d sub y divided by d, which is 5 over 0. Because the d's are zeros in the denominator. Division by 0 is undefined. So in this case here, we have what we call an inconsistent system. And that solution set is undefined. Or I should say the solution set is just the empty set. Okay, so this is an example of a system of equations. When you try to use Cramer's rule, your d is 0, and d of x and d of y are numbers other than 0. Okay, now let's take a look at this next example here. Here we've got x plus 2y is equal to 3, and 4x plus 8y is equal to 12. And let's say we want to solve this one using Cramer's rule. Okay, so in this case here, we got x plus 2y is equal to 3, 4x plus 8y is equal to 12. I'm just rewriting the system of equations that we have here. We want d sub x, and we need d sub y. Now, of course, this is x and y for your d's, the constants in y for d sub x and constants for d sub y. So in this case here, for the d's, the coefficients of x are 1 and 4. The coefficients for y's are 2 and 8. For d sub x, the x's will be replaced by your constants, which are 3 and 12. The y's are the same, 2 and 8. For d sub y, the x's are 1 and 4, but your y's are replaced with your constants, 3 and 12. And then we find the determinants for each one of those. So for 1 times 8, that's 8, minus 4 times 12, that's 8. So 8 over 8, 8 minus 8, that's 0. D of x, 3 times 8, that's 24. Minus 12 times 2, that's 24. 24 minus 24 is 0. And then d sub y, 1 times 2, that's 12. Minus 4 times 3, that's 12. So 12 minus 12 is 0. In this case, your d sub x, and your d sub y are all zeros here. So here the d is 0. The other determinants are also 0 here. So now the system of equations is dependent. Okay? And that means that there are infinitely many solutions. Okay? So when d sub x, and d sub y are all zeros, that means you have a dependent system. That means that there are infinitely many solutions for this system of equations. Okay? So that's how those are the two special cases that we talked about here for systems of equations when you attempt to use Cramer's rule. Okay? Now, so far we've been doing 2 by 2 matrices, finding the determinants. Now, let's say we want to find the determinant of a 3 by 3 matrix. Okay, and it's still a square matrix because it's 3 rows and 3 columns here. Okay, associated with every square matrix is a real number, and it's called its determinant. And the determinant for a 3 by 3 matrix is defined as follows here. Okay, now this may be a little bit complicated here. Here, the determinant of A1, A2, A3, B1, B2, B3, C1, C2, C3 is this. A1 times B1 times C3 plus B1, C2, A3 plus C1, A2, B3. Then minus A3, B2, C1 minus B3, C2, A1 minus C3, A2, B1. Now again, this might be a little bit complicated here, but there is a way that we can come up with this determinant. Now I'm going to show you one way that your textbook shows you how to find the 3 by 3 determinant, and then I'm going to show you another way. In this case, a third order determinant is defined by this. Okay, that's your 3 by 3 matrix, and then they use this column here as the number that's going to be outside the 2 by 2 matrices. Because here you have to break this up as a 2 by 2 matrix that looks like this. And then notice the signs alternate, because the first one is a plus, then next is subtraction, then next will be addition. So here we're alternating signs here. Okay, so let me explain this way. Each of the 3 terms in the definition contains 2 factors, a numerical factor and a second order determinant. The numerical factor in each term is an element from the first column of the third order determinant. The minus sign precedes the second term. The second order determinant that appears in each term is obtained by crossing out the row and the column containing the numerical factor. In this case here, if I'm using a sub 1 is in the first row, first column. I'm crossing out the first row and the first column. And this comes from what's left, which is B2, C2, B3, C3. And then the second term is the minus sign, because this is a plus, then this will become minus, and then the third one will be plus. So we're alternating plus and minus signs. A2 is in the second row, second row, first column. So we cross out the second row and the first column to get the remaining numbers here. B1, C1, B3, C3. And then plus, A3 is in the third row, third column. We cross out the third row and the third column. And we get B1, C1, B2, C2, which is this. The minor of an element is the determinant that remains after deleting the row and column of that element. For this reason, we call this method expansion by minors. Okay, that's what we're using, expansion by minors. Okay, and here's a study tip that may help. Now, when you expand a determinant by minors about any row or column, you want to use alternating plus or minus signs to precede the numerical factors of the minors according to the following sign array. In this case, the first row starts off with a plus, then minus, then plus, and then minus, plus, minus, and then plus, minus, plus. We alternate plus and minus signs. So if you were using this first row here, then it'll be plus, minus, and then plus. But if you want to use the second row, it has to be minus, then plus, then minus. All right, look at this example here. We want to evaluate the determinant of the following matrix. Here we got 2, 1, 7, negative 560, negative 431. And we're going to do the expansion by minors. So here, we got 217. I'm reading this off by rows. Then negative 560, negative 431. And here we want to use expansion by minors to find the determinant of this 3 by 3 matrix. Okay, what I'm going to do here is use the first column of this matrix here. Here's the first column that I'm going to use. And then what I'm going to do here is find the minor for each numerical factor by deleting the row and the column of that element. So if I'm using the first row here, the first element is a 2. Okay, 2 is in the first row, first column. So I need to delete the first row, and I'm going to cover up the first row and the first column. When I do that, this is my minor, 6031. So now, this will be the minor here, 6, 0, 3, and 1. Now I'm starting off with a plus, so the second one will be a minus. And then this second term that I'm going to use here, or the second element, if I'm using the first column, the second one I'm going to use is negative 5. And then I'm going to find out what its minor is going to be. Now the negative 5 is in the second row, first row, second row, first column. So I cover up the second row. Okay, I'm going to try to do this, covering up the second row and cover up the first column with my finger. Here's my other minor, 1731. I'll write that down. And then the next one will be a plus. Okay. Now, the negative 4 comes from here, from that third element in the third row and first column. Okay. So I'm going to cover up the first column and the third row. When I do that, there's my other minor, 1760. Okay. That's expansion by minors here. Now what I'm going to do here is take the determinant of each individual second order 2 by 2 matrix and then multiply it by the number that's on the outside and just simplify this all together. So now in this case here, let's start with this one. Bring down the 2 times, and then I'm going to do 6 times 1, which is 6, minus 3 times 0, which is 0. Okay, this diagonal, upper left to lower right, minus this diagonal, lower left to upper right. Then minus a negative 5 will be a plus 5, and then find out what this determinant is going to be. 1 times 1 is going to be 1, minus 3 times 7, that's 21. Plus a negative 4, I'll just say minus 4. And then the determinant here, 1 times 0 is 0. Minus 6 times 7, that's 42. Now I'm ready to simplify this. 6 times 0 is 6. Plus 5 times 1 minus 21 is negative 20. Minus 4 times 0 minus 42 is negative 42. Okay, and then I'm going to simplify this some more. 2 times 6, that's 12. 5 times negative 20, that's going to be minus 100. Minus 4 times a negative 42 will be a plus 168. And then I'm going to do 12 minus 100. That's negative 88. Negative 88 plus 68 would be 80. So, using expansion by minors, the determinant of this matrix, of this 3 by 3 matrix, would simply be 80. Okay? Now, I realize that could be a little bit complicated, but there is an easier way to do this one. And I'm going to show you how this is going to be done the easy way. It's just an alternative method here. Okay, I'm going to use that same matrix here that I just did. Let's see, 2, 1, 7, negative 5, 6, 0, negative 4, 3, 1. Okay, here's the easy way to do this, to do a determinant for a 3 by 3 matrix. First, I'm going to rewrite the first two columns of this. 2, negative 5, negative 4, 1, 6, 3. What I'm doing here is just rewriting the first two columns of this matrix. Okay, now here's what I'm going to do here. I'm going to take the determinant of these diagonals that I'm putting in green. Okay, notice I'm going to take the determinants of these three diagonals. I'm going to add them together. And then whatever that is, I'm going to subtract from it the product of these, the sum of the products of these three diagonals going this way. Okay? Okay, you'll see what I mean when I do this. Okay, let's start with these columns, these diagonals going from the upper left to lower right. If I do 2 times 6 times 1, 2 times 6, that's 12, times 1, that's going to be 12, plus 1 times 0 is 0, 0 times negative 4 is 0, and then 7 times negative 5, that's going to be negative 35, negative 35 times 3 will be a plus negative 105. Okay, now we're going to subtract. We're going to subtract each of these diagonals from lower left to upper right. Okay. So in this case here, we got negative 4 times 6, that's negative 24. Negative 24 times 7, that's negative 168. So this will be minus negative 168. Then minus 3 times 0 is 0, times 2, that's 0. Minus 1 times negative 5 is negative 5 times 1, which is negative 5. Okay. Now we're going to simplify this a bit. Now if you do 12 plus 0, that's 0, plus negative 105, minus a negative 168, minus 0, minus negative 5, you're going to end up with 80 as your determinant for this 3 by 3 matrix, which is exactly what I came up with when I did that last matrix using expansion by minors. Okay, so that's how we do a determinant of a 3 by 3 matrix, and this is probably the easy way to do this, rather than using expansion by minors. Okay, I'm going to do another one that's similar to this one. That way you'll get the hang of it. Let's say we had this one. Excuse me. Let's say we had 2, negative 4, 2, negative 105, and 3, 0, 4. And let's say we want to find the determinant of this 3 by 3 matrix using that technique that I just showed you earlier. All right, in this case here, what I'm going to do here is rewrite the first 2 columns of this matrix. So I'm going to rewrite this as 2, -1, 3, -4, 0, 0. And here's what I'm going to do. Take the determinant of these 3 diagonals from the upper left to lower right. And I'm going to subtract from it. And it's going to be minus the product of these 3 diagonals from the lower left to upper right. Going this way. Okay. Let's start with these going this way. 2 times 0 is 0. Times 4, that's 0. This one, -4 times 5, that's -20. -20 times 3 is -60. And then this one, 2 times -1 is -2. -2 times 0 is 0. Okay, so those are those 3. Okay, now we're going to minus the product of these diagonals going this way. 3 times 0 is 0, times 2 is, of course, 0, minus 0 times 5 is 0, times 2, again, that's 0. And then for this diagonal, 4 times -1 is -4. -4 times the -4, that's 16. So it'll be minus 16. Okay. And then we're going to simplify this using the calculator here. If we do -60, well, all we got is -60 minus 16. That's -76. So the determinant of this 3 by 3 matrix is -76. Okay? And also, I'll go ahead and do this on the calculator because you can find determinants on a calculator here. I'll show you how that's done on the calculator. So in this case here, if you press second and then x to the 1 for your matrix. Okay, now we're going to put in a new matrix here, so let's edit by using our right arrow key. And let's put this in matrix A, which is number 1. It's a 3 by 3 matrix, means that 3 rows, 3 columns. So we type in the 3, then enter, change that to a 3, and then hit enter. And then change these numbers here. We started off with 2, well, actually, 2, -4, 2. So we enter that row, 2, enter, -4, enter, 2, enter. Then the next row will be -1, enter, 0, enter, 5, enter. Then the next one will be 3, enter, 0, enter, 4, enter. Okay, and then to get out of it, hit second and mode to get out of it. And then you want the matrix again, so second x to the -1 for your matrix. Let's go to the math menu, highlight that using your right arrow key. Notice in number 1 you see DET. That's the abbreviation for determinant. So we select number 1 because we want the determinant of that matrix that we entered, that we saved in our calculator. So go to second, x to the -1. We saved it in A, so we select number 1. So we're finding the determinant of A, and then we're going to hit enter. That determinant came out to be -76, which is exactly what we came up with in that when we did it by writing it as 2, writing the first 2 columns and then finding the determinants using those diagonals. Okay? So that's this particular section on determinants and Cramer's rule.